You are listening to Neurosalience, the OHBM podcast.
Welcome to the OHBM Neurosalience podcast. I'm Peter Banatini, and here the challenges, findings, and issues related to neuroimaging are discussed with researchers in the field. On this episode, we have a great wide-ranging discussion with the 2021 Early Career Investigator Awardee, Dr. Chao-Gan Yan. We talk about a little bit at the beginning, we talk about his career path, the highly impactful work he's been doing over the past decade, as well as some of the most challenging issues with fMRI, dealing with things like motion, subject variability, the challenge of finding biomarkers, and what he does pretty much is, what he has done is designing the right packages that help both the beginner and the expert alike. He gives some really good advice about what was essential to him to get where he is today. It also becomes clear during our discussion on why he's the winner of the award this year. You know, while his work speaks for itself, he has a bunch of papers with huge numbers of citations. His approach and kind of his mastery of the issues and understanding the issues clearly comes through in this conversation. Some of the issues are truly difficult. For instance, finding the neural correlates of various disorders. He actually understands pretty deeply as comes through. He gave some really insightful thoughts on why we're having a hard time with that. There's variability from day to day with each subject. And then, we bring up the thought of, well, maybe these disorders manifest themselves at a different scale that fMRI is sensitive to. But he's not giving up hope, certainly just the opposite. He's charging ahead because he feels that, in fact, there is a place for fMRI in clinical applications from day to day. And specifically, he talks about some of his really exciting work, recent work trying to understand neural correlates of depression and using neuromodulation potentially to using transcranial magnetic stimulation to suppress these areas that are unique to depressed patients. So enjoy the podcast. Welcome to the OHBM Neurosalience podcast. I'm Peter Banatini, and I'm here to discuss the latest topics in brain imaging and with leaders in the field. And today, I'm very fortunate to have the winner of the 2021 Organization for Human Brain Mapping Early Career Investigator Award, Dr. Chao-Gan Yan. Dr. Chao-Gan Yan is a professor at the Institute of Psychology at the Chinese Academy of Sciences, and he's the director of the Magnetic Resonance Imaging Center and the director of the International Big Data Center for Depression Research and the principal investigator of the resting state fMRI lab located at the Chinese Academy of Sciences. Before he joined, the acronym is IPCAS. Before he joined IPCAS in 2005, or IPCAS, IPCAS, I prefer to say, in 2015, he worked as a research scientist at the Nathan Kline Institute for Psychiatric Research and a research assistant professor at the Department of Child and Adolescent Psychiatry at New York University School of Medicine. So Dr. Yan received his PhD in cognitive neuroscience from State Key Laboratory of Cognitive Neuroscience and Learning at Beijing Normal University in 2011. His research mainly focuses on the resting state fMRI, which he terms, and we're still coming up with a good term for it, to R-fMRI, computational methodology, mechanisms of spontaneous brain activity, and their applications to depression. And I've also noticed among his papers, he studies other disorders as well. He has addressed fundamental methodological issues such as the impact of head motion, standardization, and multiple comparisons on the study of resting state functional connectomics. He also developed data processing and analysis toolbox, which he's produced some amazing papers with those, which we'll talk about, for R-fMRI, DPABI, DPRSF, the latter having been cited over 2,000 times. So he's extremely well cited. His papers have had extremely high impact because they're so useful. He initiated a Chinese consortium for big data, brain imaging, and depression, performed big data study of depression and neuroimaging, which was a PNAS paper in 2019, and studied the brain mechanisms of depression through longitudinal study of animal models. He published over 60 articles, 30 as corresponding author in many prestigious journals. And his work has been widely cited, as I mentioned, in the scientific community. His 6 of his first author corresponding author papers ranked as ESI top 1% highly cited papers, 2 of which were ESI top 1%. Okay. So he's also been ranked as a 2019 most cited Chinese researchers by Elsevier. And he currently serves as the associate editor for Neuroimage Reports, which is a new branch of Neuroimage, which we might talk about as well, and serves on the editorial boards of Neuroimage and Journal of Neuroscience Method. So thanks for agreeing to be on this podcast, and definitely congratulations on this award. This is a big award. This is in my opinion, this is the most prestigious award next to the Glass Brain Award at OHBM. It has a long storied career of different names, of different sponsors, but over 25 people have won the award. And you actually just we're having this podcast over a month before OHBM and plus, and so this is still a secret right now. But when you got the email or call or whatever, how did you feel when you heard you won it?
It's a very great news that I've been joining OHBM meetings since 2009, so it's about 12 years, and every year I will join the OHBM and look at the opening ceremony and look at the awardees of the Young Investigator Award and now Early Career Investigator Award. There are so many big names like Carl Friston, like you, Peter Bernardini, like Paul Thompson, like Steve Smith. And today, I finally become one of them. So this is a great honor. And to me also, this also means a lot of responsibility. That means I need to do better to deserve this honor, because I need to try my best in my future. So this is a really great news, very inspiring.
That's great. That's great. Yeah, no, it's actually, I remember when, you mentioned I received the award way back in 2002, and it was pretty, it was a very, what I would call a heady experience, where you feel, even then it was sort of like, the likes of, Carl Friston won it first and other people. And the fact is that it's really a nice award in the sense that it's not in a, you have a certain number of metrics and you win the award. It's like a committee really thinks carefully about what true impact you've had on the field. And definitely, I've spent the last week or so, sort of going over, your papers. I've seen your papers in the past, but it struck me that, you've been extremely busy and extremely productive, not only producing papers, but producing useful papers and ones that are, really thoughtful. And I also have to say, just right up to the front, that reading your papers was amazing, because not only were they, edifying and interesting and stimulating, but they were extremely clearly written. I have to say that that's a skill and something that's not emphasized enough at not only in the OHBM community, but science in general, is the art of writing very clearly. And I believe that you do that exceptionally well. So So definitely congratulations. And I think that has an impact in your papers. People read the paper and they understand it immediately. And they'll use it and implement it and cite it then. So, okay, well, before I get into your work, could you tell us a little bit of your background and maybe what motivated you and how you ended up where you are now? I noticed you were in cognitive neuroscience, but obviously you do a lot of methodology, and so you obviously had to learn a lot of technical skills as well. So I'm kind of curious. Yeah.
I was born in a small village in South China, but when I was a little boy, my dream is become a scientist. So this is a long purchasing dream. But there's something happened in my life trajectory, so I didn't go there directly. And somehow I become a mathematics teacher in a middle school. And during that time, I think maybe someday I still want to be a scientist. So that's my first job. But later I also go back, enter the college, study automation. It's like EE in the US. So that's a lot of programming and signal processing. That's fundamental thing. And after my college, I want to go to the postgraduate program. I want to go to Tsinghua University, which is the top university in China, and go to the entrance exam. But I missed by some points. And later, Yu Fengzhang emailed me that I have a program that we have vacancy. Are you interested? And I went to Beijing Normal University at that time and talked with Yu Feng. And Yu Feng said, I know you want to, your background is automation. It's somehow go to engineer, but now we are doing brain science. If you're interested in science, you can come here. And I said, my dream is become a scientist, not an engineer. So I went to Yu Feng's lab and studied cognitive neuroscience. And mostly is the rational self methodology. So that's why I built my methodology background. And also I found I needed to build some tools to myself to use because there's a lot of software is not so convenient. So I built my first version. I called it DPAS, DPASF. I just will use a unique name, but it's difficult to pronounce it. Let me make people to remember. And then later, after my PhD, I joined NYU and Nathan Kline with Mac Milham and Javier Castellanos. And there I deepened my skill in R-fMRI. And maybe later I can talk about that. I also did something with the animal, like monkey recordings. That's why I visited David Leopold. But that's not some successful experience, but it's important for my life. And later I joined the Institute of Psychology, Chinese Academic Sciences. And now I'm more focused. We are doing residency a lot of time, but can our work to be useful? So that's why I really hope my work someday can use to help the patients. So that's why I built the depression consortium to see if our work someday can help diagnosing the depressed patients, and also if we can provide the targets based on fMRI for the TMS treatment for depression. That's my recent goal.
Okay, that's and definitely you brought up a couple of things that I definitely want to talk to you, like for instance, using big data, converting it clinically, and using your clinical application of targets for TMS. I think that's one of the probably best chances for fMRI to be useful in that regard. So as far as skills, you mentioned, right, obviously you had to learn, some computer, obviously, you did have a lot of technical skills coming in. And so I actually think that the people who make the highest impact in the field are the ones who, certainly a lot of different people make impact, but I think in general, if you have technical skills and if you have a sense of good questions, that's usually a really good combination. You don't want to necessarily just be relying on pressing buttons of some package, although at the same time, you can do good research that way. And actually, a lot of your tools, as I sort of delved into your papers, are sort of meant as sort of not only to help, not necessarily only to help the most sophisticated user, but to help the less technical user sort of make correct inroads to fMRI. So and other aspects of brain imaging. So and also Nathan Kline is a great place to learn. They have Dr. Castellanos is extremely insightful person. So you've been productive. You've been extremely highly productive. I mean, I'm surprised you didn't win the award earlier, because you've been so impactful for now over a decade. And so what would you say, before we get into some of what I thought your more, I mean, obviously I look at your most highly cited papers, but there's some other really interesting ones elsewhere too. But what would you say are your most significant contributions to the field so far?
So for me, I think there are three intertwined points. So firstly, I do methodological studies, like for example, when our field faced some impact or something like head motion back to that time, 2012 and 2013, and the multiple comparison correction in 2016. So then I would think, oh, how should I do? Which one should I choose? So I needed to do some research that to compare, to figure out which one myself should to use. And once I figured out someone is good to use, I integrate to my software. So this is my second one is intertwined with my software. Because my software is somehow popular, then the users will ask me, Dr. Yan, they said head motion is a big problem, and the reviewers ask me, how should I do? Then I need to do that research. And also multiple comparison correction, they also asking, what should I do? Because the reviewers are asking, so I have to do the methodological study and integrate into software. And then the users is very convenient to use our recommendation. And usually the reviewers mostly are satisfied with our recommendation. And because they use our software, they use the correct one, then the study is going very straightforward. So this is why I build the methodological studies and build the software. So they are intertwined and make myself, I'm busy because I need to fulfill the user's need and also do the scientific research. And based on these 2 points, my methodological studies and my software, I built some reputation in the field. Then I want to make myself useful. So that's why I built the depression consortium, because most of the people are using my software to analyze the data. So I emailed them. So we want to build a depression consortium. As you used my software to process your data and publish your papers, could you share your processed data with us? And we can do some big data research. So I first initiated in China, and most people answered yes. So that's why they use my software to process the data, use a standardized protocol at the local. They do not share raw data because of some concerns, and share the final process data. So this is how we build a big data consortium, and we did some paper in PNAS. But more importantly is we openly shared the processed data. So it's about 1,300 MDD patients and 1,100 controls. Is the biggest openly shared data for depression. So this also attracted lots of people from other fields like machine learning. They come to use this data. And together, I hope in the future, we can, like myself, I don't think myself can address the big problem eventually. But if we keep this open and invite the other investigators, maybe together, we can do something useful to the depression. So this is from the methodological study, from software, and then later to the implementation. They are each other intertwined.
Yeah, it seems like they all sort of work together in a sort of synergistic way as well.
Yeah.
So what would you say? And so I noticed that your early versions were in MATLAB. But I mean, as far as are you still working on trying to? Do you think it's useful to potentially try to convert everything to Python, for instance, or other sort of platforms for ease of use or more or better dissemination?
So initially started with MATLAB because it's once I build something, it's also okay for Windows, for Linux, and for Mac, and build stuff from there. But up to now, when I release my software, I always compile them. So for people who do not have MATLAB, they can use I release a Docker file. So once they import the Docker, they can run the software without MATLAB. They just use a Docker, because within the Docker, there's a MATLAB runtime machine. So that compiled program can let them use without MATLAB license. So this is the way we going forward. And also in the future, we do have some plan to build into Python. So for example, recently we do some machine learning studies, like deep neural network for, we call it brain image net. We built that in Python. And I think mostly in the future, there are lots of tools we build in Python. That's another branch. But I'm not sure if I will convert the full software into Python. That's a lot of work.
Yeah,
but usually people will not fund it for that. But I think the new functions we can build in Python. But the old ones is always compiled. So for people who are interested, actually there are lots of people interested in using our software, and some of them are using Singularity. And they also made some good suggestions that MATLAB runtime machine need to expand the zip files. So they suggested some commands in my Docker files to unzip them, and they can use in Singularity. So
that's good. That's good. And also right. I completely agree. Trying to go back and redo everything doesn't seem like the best use of your time, because it seems that and as you showed with your, at least 4 papers, you have, dparsif, rest, dpabi,
I call it dpabi.
Okay. And then Rest Plus just recently that you've been part of. So, I mean, it seems that, and this is one thing that in some sense, I mean, it's a tricky thing to capture in some sense. It's that you have this package that really does help people do the right thing in their analysis, and I think that's really impacted the field. But at the same time, the analyses keep on evolving, and people always, are still comparing methods, or maybe trying new ones and realize something works a little bit better, or, maybe works with different pulse sequences better, or things like that. So it's a tricky, how do you think about the balance? I mean, some people, and also just as another part, you have all these other packages that are like suites of tools, like AFNI, or, FSL or SPM or Brain Voyager or whatever, that they're all great. And I think what differentiates yours, and correct me if I'm wrong, that yours sort of, doesn't have, doesn't just say, here's a bunch of tools. It has a lot of tools, but it says, this is the best thing to do, or this is probably the best thing to do. And you'll be okay. You'll be good doing this. I think that's what I gather as a difference. Is there more of a nuanced difference, or is there more of an obvious difference between your packages and other packages that are out there? I'm not sure if.
So when I design my packages, there are always thought that should use for novice users and for sophisticated users. So I always separate the building of GUI, the GUI system, and the pipeline system. So the GUI system is always just citing the parameters, and we have a default sightings for that, what we think of the best. And the people can use the GUI to set up the parameters. If they are novice users, they just use a GUI, they click run. But for sophisticated users, the back end is script, is a separate script. So they can always use the scripting to set the parameters and have lots of freedom. So that's why the novice users, they can use a GUI, and the sophisticated users, they can just use my scripts and allows to run that. So that's from the design. And second is, I think is because, like you said, is we recommend something we think it is good, and we keep updating that, because once there is something new, like Eklund 2016 paper said the multiple comparison issue, then we need to develop something that we think which we can recommend to the users. And we compared, and we found the permutation test with Steve Smith and Tom Nichols' TFCE is performed pretty good. Then we think about how can let users have no security knowledge, or maybe he's just a doctor in the clinical settings, doesn't know any programming. How can he use the permutation test? So we started build a GUI. It's very easy to use, just one click. We call the Winkles Palm to do the back end. And what he needed to do is, because he just click and use the results, and very easy to use. I think that's why lots of people are using. This is also, I think, related to my background, because once I was a mathematical teacher in a middle school, I need to think about, okay, the student may know nothing. How can I best teach them to learn the math? And now is maybe the users know nothing about programming, and they know nothing about, maybe they know little about neuroimaging, but how can they do the things correctly? I need to think about from their way to design, and also needed to design a way how to best learn that. So when I design the software, I'm always designing the course, because I think make them very easy to learn and easy to use. So when I'm building the tools, at the same time, I'm building the course. So I think this is why lots of people using that.
Yeah, I think I agree. And I think you're actually onto something with regard to, definitely that's a, it's funny because people who, there's different philosophies. People want to build a lot of options and a lot of flexibility, which is also good. But also I think that a lot of the field just wants to know what to do, and they want to understand it well enough, but they don't really need to know and think about it every single time in some sense. So I think definitely, and this is a big bottleneck for actually clinical implementation, that we don't have so far the vendors, there's no fMRI processing suite yet, and so it's a really hard problem because it is a hard, fMRI is much different than standard MRI, and to use it clinically, well, obviously first to use it clinically, for targeting, I think that's a great use. And we might start talking about the big data in a second, but another further down the road goal is like biomarkers and looking at individual subjects, and maybe and then there you really need some, people are, I think the answer will probably be cloud-based computing, where it just kind of goes and you have your, and you could probably, if with your skills in automation, as far as that's concerned, just having an automated sort of suite that does this. I think that's what fMRI needs right now. I mean, one aspect of it for clinical implementation. So and okay, so let's maybe switch gears slightly and talk. I mean, you mentioned in your papers, you implement various motion correction, and it's interesting because motion. It seems like if you were asking somebody, well, we can do all this sophisticated processing, but we can't get rid of motion. Well, we can do it pretty well, but nowhere near perfect. And so either you try to mitigate it, or your software and others help recognize it. And it's still a problem. So what do you think? I mean, we're pretty good right now, and thanks to your tools as well, but do you think we'll ever be able to fully correct for motion? And if not, why? Why is it such a hard problem?
When doing the motion work, it's very interesting that back that time, like Jonathan Powell and Ted Satterthwaite work and Van Dyke's work, people draw a lot of attention to motion. And at that time, I'm thinking about how can we partially address the concerns. And I read a paper back to 1996 by Carl Friston. he's talking about this kind of stuff very early. And he uses the magnetic equations. And at the end, he derived the equation using the tampons, the tensor before and the squared atoms. And the previous people do not use this formula or do not use these squared atoms. And I think because Carl Frister modeled the spin history, because I think the most difficult part for fMRI for high motion is the spin history, because we excite something like there, but if they moved, they have changed somewhere else. So that's why I think that's why Carl's formula works pretty good. So after that, from my paper, and also Ted Satterwhite also mentioned about these squared atoms. So lots of people are using this Carl Frister formula a lot of times now. And I think in the future, head motion is still a lot of problem. And just yesterday, I talked with some Chinese manufacturer of the MR machine. He's talking about probably we can build up something from the machine-wise. For example, if we have a pointer on the brain, and if we know the exact motion at the real time and in the scanner, probably they can compensate the spin history real-timely for the EPR band. Maybe, I think some people are doing that. I think that is probably will be a good way in the future that they monitor the head motion, not using imaging, not using the fMRI image, but using some target, and using that to compensate the RF or compensate the spin history. And because if we do the children study that really have lots of motion, it's very difficult to control them. And I think that might be a future direction.
Yeah, no, right. The whole spin history thing. Yeah, you're absolutely right. I do remember, right. That was very big. Oh my gosh, 20 years ago, 15 years ago when Carl Frister, and it's interesting. It sort of died away partially. I think I remember it trying to implement it, and one potential caveat in that, and it's just a matter. It's not an intrinsic problem with the understanding of spin history, but something about the algorithm also got rid of bold effects as well sometimes, because they have like a slow effect that's like a spin history effect. It sort of like has that time constant, so it sometimes gets rid of bold, but it's still, I think it can be tweaked to not get rid of bold. I think you're right. I think it's spin history that we're not considering, because definitely the brain isn't like this rigid object that just it shears, and when you collect it as you're collecting each slice, and but also I think that the magnetic field changes as well. I mean the image warping changes with motion as well in very subtle ways. So yeah, I mean it's a technically, and it's a problem that goes right down to the physics. And
personally, I think mathematical in the physics way, seems this is a problem can be adjusted. It's not just everything leave to us at the post processing to deal with the head motion effect. I think at the front end, from the machine wise, if they can collect the real time head motion, they can do a lot of things to make a signal much better. But I wonder, probably because this is not too much profitable for them, because they're most profitable is for the clinical patients, and for the fMRI currently do not make lots of money for them, so they didn't put too much effort on that.
Yeah, no, we had a whole podcast talking to vendors. Like, the problem with fMRI is that it's benefited from the fact that clinical MRI is so useful, but it can't influence what the vendors do because there's no clinical market for fMRI. So we're just like riding on the back of this massive clinical MRI business, and we're just sort of taking what scraps they can give us and using them, but they don't. Yeah, I think there's room for small companies. Like there's this company, Connecticore, that developed just what you said. They have like a Moire pattern on the head, and it kind of and it works better for like structural imaging, and structural imaging has a much lower threshold for images look good and they look a little bit better and people are happy, but with fMRI it's like that could screw up your whole study if the criteria are much higher.
Yeah.
So it's hard. It's hard, and I definitely and along those lines, I really loved in your paper on interindividual variation in 1,000 connectomes. I loved your laying out of all the possible things that can cause variation. And you mentioned everything from scanner make and model, down to physiologic things, environmental things, experimental related variations. Really nice layout of this, a nice review of the state of the art of the field. And one thing that and I really liked how you suggested that certain ones made more of a difference. And I just wanted to talk a little bit about because of working with Nathan Kline and also working with big data. And I just had a recent conference with the NIH last September on they have all these consortia and they do across different scanners, and they try to keep the vendor more or less the same, and they're even finding these massive site effects. And it'd be nice to try to further standardize that as well, to further pull out. The goal is to pull out these small effect sizes, and who knows what is causing that. And it may not be related to any of these. It might just be related to the population variation is too big. But yeah, having all the vendors, once again, trying to get them to work together, or maybe having an offline recon and standardizing that or something would be useful. But in this paper, so one thing I was curious about, and this I think is an important point, and you mentioned the difference between additive noise and multiplicative noise. So what would be the difference between those in that sense? How are they different?
Actually, back that time, that the combat doesn't developed in the field yet. And my lab now is still, I think the suggestion I made in 2013 paper is not good enough. So my lab is still doing on that way, because we have lots of big data studies. We have data come from many sites and many scanners. How to best standardize them is still a challenge for us. And there's some study my lab is doing. One is using the linear mixed model, and another is we are trying to improve the combat model. So the combat model is also modeling the additive noise and the scaling noise you mentioned, because there's one thing is additive, so it's have an impact on the mean, and also have a scaling effect is have the impact on the standard deviation or on the variation. So combat is based on the data we have, the error term, the residual, and we will estimate some super parameter that to help us best to adjust additive noise and the scaling noise. And we do have some improvement on that. My lab is still doing. We do some principal combat, but that doesn't very finish yet. But we still put a lot of effort on that way, trying to better standardize data, and we have multiple data and how to best combine them. And my lab also scanned some data that we scanned about 50 subjects for around 3 scanners. So scanner 1, scanner 2, scanner 3, 50 same subjects. And we are thinking about if we have a good standardization tools to standardize them, then the 50 subjects after standardization for the 3 scanners should look pretty similar. Or we call it the ICC should be very high. So we are trying to use that as a benchmark, because we do not have benchmark if you have scanned different subjects from 10 scanners. And even you have lots of algorithms to standardize them, you don't know what's the ground truth. But if all the same subjects, then a very simple thought is after standardization, they should look very similar from the different scanners. So that's what we are doing. And we do find something good after revising the combat, but we are still trying to test, and maybe we'll submit soon.
Okay, that's really, I mean, it's in work that only a few groups, can do really well. And I think definitely your group is one of them. And that's important work too. It's one of those things that people, it's not like, right. I mean, we'll get into your work on depression, but it's important to have these, basic, because I think fMRI is going through something of a, I wouldn't say a crisis, but some sort of a feeling like, is there too much variation to actually say anything that's clinically useful? And this sort of study, I think, is really fundamental to answer that question. And another source of variation, I also noticed, another paper that you had in parcellation-based connectomics. You were on it, but Cameron Craddock was the first author, and Vogelstein was on it, and Saab Jabi, which was on it, Nature Methods in 2013. It was, I thought that was also a really nice, simple, straightforward review. But it brings to mind at least something that's been on my mind a lot. And it seems like more and more resting state studies are, you first parcellate, they're first parcellating the brain, and then they're having these connectivity matrices, and they're comparing the matrices. And to me, a huge problem in the field is, and this is kind of how fMRI works, is it sort of iterates, does something for a while, then everyone says, wait a second, is that the right thing to do? We actually have to back up and see if that's the right thing to do. And this is, I think, one of those things where parcellating is great. And I think it's really has advanced a lot, and it's a powerful tool, but trying to compare across subjects and morph the brain into a parcellation, a common parcellation structure, it seems that the field can do that at very low resolution pretty well. But the higher resolution you go, or the more finely you parcellate the brain, it becomes really messy, and it's really hard to pool data. I'm curious if you have any thoughts on that. And if it would be great to develop, nice tools to do that really well. Not only to parcellate, but to warp the parcellations based on cortical anatomy or functional differentiation. Who knows?
Yeah. I think there are several thoughts in the field, or several recommendations. First, functional parcellation is much better than structural parcellation, like Steve Smith's work in 2011. So that's people using the Cameron Craddock's parcellation, or now Schaeffer's parcellation, or Glasser's parcellation. The second, people think about the surface parcellation is better than volumetric parcellation, because the volumetric parcellation, you have the gray matter, you have the white matter, you even have a CSF average into the parcel. But on the surface is we are not average in the white matter and the CSF. So that's why myself is going to surface and using Glasser and using Schaeffer from Thomas Yale's group. And the third thing is important is people thinking about individual parcellation is better than group parcellation. Then there is a problem is how to do that very good, how to have the individual parcellation. I think Thomas Yale or Hersen Liu is doing some work on that. But up to now, I'm not too much convinced. Anyway, I'm not too much convinced that warping back that into individual space is reaching the standard that, okay, I will talk to everybody now using this method. Okay, I will integrate it in our software. You can use this individual parcellation. I think there's still lots of work to do, that individual data, there's lots of noise. And I think eventually maybe we can reach some consensus how to parcellate at an individual way. We use a group parcellation as an initial point and at the end, because when we compile the subjects, I think we still have some concerns. So that's what myself, maybe in future we can do some comparison. We can develop some individualized parcellation algorithms or tools. But up to now, I'm not too much convinced yet. But I think in the future, maybe there will be some consensus.
Yeah, I think I agree. And I think actually, as we learn how to parcellate, in such a way that we can compare subjects or come up with some sort of transfer function. I think the variation in individual subjects' parcellation, that function might tell us a lot about individual subjects as well. I mean, not only the resting state, once you get the information from the parcels, but the actual transformation of the parcellations, that's a biomarker in itself, I think. So that's really cool. That's interesting. That's great to hear that you also agree that it's sort of like an open, it's an open, ongoing research area. That might end up being really hard, and because the brain does become more variable as the parcels get smaller and things are almost intractable. But I think there's hope. But okay, so I'm just going to switch gears on what you've studied as far as with your tools. So, I mean, you've looked at, your main thing that you're looking at now is depression and potentially the treatment of depression, rumination, schizophrenia, and antipsychotics, and autism as well. You delved into a little bit. Regarding depression, it seems that, do you want to sort of kind of summarize your findings or your, what you found as far as how it's useful? Can you extract individual information? Can you say a person, are you able to, you're starting with depressed people and you're finding the differences, and obviously you're looking at interventions, but can you start with a number of subjects and say, oh, this person's probably more depressed, and this is what we need to do? And so I'm kind of curious what your perspective on that is.
This is my goal, but I'm little depressed when studying depression. That is, for example, my lab, we built some deep learning algorithms. We can predict one subject is female or male with a confidence of 95%. Anybody from any scanner we can see. And also we built a very good models for Alzheimer's disease. We were highly confident that 90% any scanner from anywhere, because we use individual tests that the model never sees this kind of data. We have this kind of accuracy.
And that's even for that's based on the function and not just the structure.
No, not the structure, but also for MCI, we can predict if he or she will convert in the AD using deep learning model. But even with this good performance, when we apply to the psychiatric disorder like depression, like autism, or like ADHD, it's very messy, the results. So this is maybe some kind of philosophy question that do the patients with depression really have a biomarker in the brain? But I still believe in that. That's why I'm still doing that. So that's why we didn't find that it's maybe the structure image didn't reflect that kind of change. So we need to go functional. So that's why we are doing a lot of functional now. But we do have published some papers. And that's something I really believe in is the medication will change brain function, will reduce brain function connectivity. It's because this in our big data study cross-sectional, we found this kind of effect. And recently we follow up with the longitudinal study. We have 8 weeks treatment and we've compiled the brain, the connectivity. We found the same exact effect. But once we turn to individual, it's difficult to see. And I think there's one thing is rational state good enough? So that's why my lab slightly changed our paradigm. It's not only rational state. We also studied rumination, because rumination is an important symptom for depression. They always ruminate why this shit happens to me. What part of myself or what my personality makes me just so dumb in the world. So they always have this kind of confined thinking style. So we induce them thinking in that style, illumination, because in resonance state, we really do not know what they are thinking about because it's too open. So once we induce them into a illumination state, so that's my lab currently is doing is, I hope or we think we will better find some biomarkers for MDD patients compared with healthy controls. And also my lab is hope with using the illumination paradigm, we know where the brain have the control, focus, let the people illuminate, and we use that target probably for the TMS stimulation to release people from the very painful illumination. These are all recent goal of my lab. And another way is we also collect data when they are resting state. We have bought some MR compatible active denoising microphone. They will speak out whatever comes to their mind. But because resonance state is too open, we do not know what they are thinking about. So we ask them to just speak out whatever comes to your mind, speak out. So that's why we are trying to linking the thinking stuff to the open-ended resonance state. So this is also my lab is doing. So we are trying to, resonance state is good, but maybe it's not good enough. So maybe in the future, go to clinical application, we do some modify, we do illumination, or we ask them to speak out what they think about, and probably some thoughts and some of the brain activity can have the biomarker.
That's a really great idea, and I haven't thought of using rumination as sort of like, rumination is sort of like a secondary effect of, if you're depressed, you ruminate more, and then I guess the challenge would be to separate the involved with the language areas involved with speaking versus speaking in a way that's about what your ruminating thoughts are, which is probably pretty easily differentiable. I like that. And in other groups, and it's funny, you mentioned a few things exactly along the lines of, part of what my own research is we're trying to sort of look at resting state and then sort of periodically asking them what they're thinking. I like the idea of sort of in between, sort of telling them to just speak out freely. That's a great idea. Some people use movies as well as sort of a stress test. Having depressed movies, they react maybe more to them, or happy ones they react less to, and who knows? I mean, I totally agree that resting state's cool, but we might be throwing away power just by letting people just do whatever and not knowing. It's best to kind of have a handle on something.
Yeah.
That's great. I really like that idea. And then the idea, of course, like you mentioned, and actually I wanted to just back up really quickly. What you were saying is really interesting. The question of, and this is actually a really important question, and I don't think anyone really wants to confront it, is that, I think everyone agrees that, disorders somewhere in some way have a physical manifestation in the brain. It may just not be necessarily on the spatial and temporal scale that we're looking, potentially. It might be much more obvious at completely some other, at the fine temporal scale or at the neural to neural scale, who knows? And it might just sort of all mix together at the scale we're looking, at the spatial scale and temporal scale we're looking. So that's an interesting point. Yeah, so I think it's there. Yeah, and that's actually what makes fMRI fun, is that we're trying to sort of, we have these messy tools. We're trying to dig in and see if we can see something related to something. We know it's there, but it may not be. fMRI might not be the right tool, but it might be the right tool if we are clever enough, like you're saying, to come up with the right probes to pull it out in something that's useful. So great. I also wanted to get into, so you're also doing, and I think I agree with you that this could probably be the best application of fMRI, is that you come up with, even with group studies, you come up with areas or networks that might show some hint of disruption. It doesn't have to be super significant, but and so if you try to modulate those with TMS, are you doing TMS as well to try to
Yeah, my lab is starting doing that, and we have a collaboration company. They built up a robotic arm. So they address the first question. Once I know somewhere to target, the robotic arm will move the TMS coil to target them. Because for humans, if we manually locate, there are lots of different things to, if we really target that thing. So the robotic arm can do that.
Okay.
Stimulate the correct, the precise target area. But the open question is still there. Where should we ask the robot to put the coil to target? So this is, I also have some initial collaboration with Mike Fox and also Nolan Williams at Stanford. And we are talking about, Mike Fox has a theory that SGACC anti-correlation or DRPFC. And that's maybe a good thing to try. But myself, I'm thinking about the illumination because I talk about with lots of depressed patients. They have lots of things annoying them, like the anhedonia, cannot feel happy, or they have anxious. But lots of stuff, the illumination makes them very painful. So I think if we can find the TMS to disrupt the illumination circle, that might be a very good way, helps them to back to normal. So that's why we developed the illumination paradigm. And we did find some illumination that the very reproducible pattern in normal controls for the default mode network nodes. And then we were trying to find that, what's the difference on the depressed patients. And my lab is planning to use that as a target to do the TMIs. And this is still ongoing. And hopefully, maybe we can have some preliminary results soon.
Yeah, and actually, I just had Michael Fox on the podcast about a month or so ago, and it was interesting because I was trying to ask him, and he gave a good answer, but it's still not clear to me that what TMS, not only what TMS is doing, it's disrupting depending on the frequency. And you disrupt this network, but it's only transient. But it's somehow, if you do it repeatedly over, week to week, over time, that transient effect sort of builds, and it becomes a permanent effect. And that's just basically long-term potentiation or just learning in some sense in that regard. Is that the idea? I mean, that's the thought. You have to do this therapeutically over time.
Yeah.
Interesting. And it's kind of like behavioral therapy where you're showing something and then you interrupt it with something else. And so you lose that association, or you gain an association, who knows? That's great. I think that use could be potentially quite clinically, it's a good avenue to go down. So, we already talked a lot all the way through what you're working on now, and also your additional tools that you're thinking of developing and obviously implementing. And we may maybe touch on this briefly, but I'm kind of curious in general what your thoughts, aside from things like motion, big data, trying to get small effects, looking for actually trying to bring group studies to individual, to then biomarkers, to what do you think the biggest challenges aside from that? I mean, maybe those are all of them, but are in fMRI or brain imaging are today, as far as that's concerned?
I think the biggest challenge is we have one subject, scan the first round and scan the second round, or scan today and scan tomorrow. And if we use the Mac Fox formula that use SGACC anti-correlation, it may be different from the first day to the second day. And how can we tell the doctor, okay, you should stimulate the first day, the most significant target, or the stimulate the second day? So this is the biggest challenge for individualization or for the clinical use, because I know some people now, they said scanning very long time. If we scan 1 hour, we may have very reproducible place. But I think that's what I'm trying to do is I think probably maybe resting state is too open. Or it's noisy. So that's why we go to rumination, or we go to ask them to speak out and find out if there is some rules or something that we can make this better reproducible for one subject. I don't want, today I tell the doctor, tumor here. Next day, oh, the spot maybe changed, we should spin where? And so I think this is the most challenging thing, that if we want to make fMRI a useful tool for clinical, it should be like your blood pressure, or like the COVID-19 virus. If we want to have a COVID-19, the disease, that must be one thing, is the virus. So.
Yes. Yeah, I totally agree with you. And it's interesting that you bring up blood pressure. That's one of the, the best, blood, just that number is a huge indicator of all kinds of things. And it's there's tiny deviations, but it's really consistent and it's really rock solid. And I think you're right. I think fMRI, maybe we have to go back to doing more studies like Russ Poldrack did with his myconnectome study, where he scanned himself over and over and over again. And really get a handle on all these variables a little bit better to figure out, because physiologic, time of day, what you ate, how much sleep you had, all kinds of, or what movie you saw the day before, who knows? There's certain things that will vary, there's certain things that won't, and of course that's dangerous, because you can go down some sort of weird rabbit holes of chasing every single possible variable. So you have to be really smart about it. But yeah, no, it's both challenging and exciting, and no one would expect the brain to be less complicated than we thought. And so it's getting more and more, complicated. So that's good. Well, the last question. Okay, so we're about to wrap up, and so the last question I wanted to ask you is just generally, you obviously thrived very well all the way through graduate school. You probably had some input had from mentors, and you probably made some really good decisions on what to do. So what advice would you give someone like in graduate school or doing a postdoc, aspiring to someday, win the Young Investigator Award, or at least make an impact? What advice, what do you think worked for you as far as that's concerned?
I think the first one is perseverance is very important. The second one is don't feel down when you think you're failed, or you think, oh, this effort totally doesn't make any sense. Someday they will pay back to you. And I have do lots of things and with no outputs, and I think totally wasted my time. But eventually, someday they come back to me. Okay, I checked that direction, and that some experience now is useful for me. Although, for example, like me myself, I spent 2 years trying to study monkey neurophysiology, and I have no publications on that way. And still, for me, nothing output for that 2 years yet. But I think in the future, that will pay back to me. For example, I also have some cooperation on the ECOG, on the intracranial neurophysiology. This is totally because I have 2 years on the monkey neurophysiology study. It's not a payback yet, but in someday in the future. So that means I want to say to them is every effort will make sense and pay back to you, and don't feel down.
That's great advice. That's great advice. And that's advice that I think even senior scientists can follow as well. Yeah. Well, this has been great. This has been really useful, I think, for a lot of people. And I wish you all the success in the future, and I'm sure that your trajectory is going to keep on going up, and I hope it does, because that will help the field and even more. So thank you very much for coming on this and talking to us, and or me. And once again, congratulations on a very, very well-deserved award. This award is extremely prestigious, and you certainly deserve it. So thank you.
Thank you very much, Peter. Thank you very much for giving me an opportunity to talk about this kind of different thoughts.
Well, it's been fun. It's been fun and useful. All right, thanks.